Welcome back to part 2 of finding volumes of revolutions. This time, we're no longer going to be using just disks, but we are instead going to be using washers. What's the difference, you might ask? Stick around, you're going to find out. So the first thing that we're going to see is that we're going to combine the ideas that we've had in this mini unit. First off, we started off when we were finding the area between two curves. We always knew the area underneath one curve, and we could always find the area underneath the second curve, and naturally it made sense to subtract to find the area between two curves. So we always had the area between the two curves was going to be the outer function minus the inner function, dx, from whatever our endpoints were going to be. And we always found those endpoints of our interval based upon the intersection points of that curve, or of the two curves, excuse me. Next, last time we saw that the volume of revolutions with disks. Volume of a revolution started off thinking about we had all of these circles, and we know the area of a circle, as you can see here, is pi r squared. Our radius was going to be the distance from the x-axis up to the level of the curve. So when we had the volume of revolution, our volume was always going to be pi multiplied by a to b being our limits of the curve, either what's defined or what's given to us, or the intersection points, pi r squared dx, or whatever our direction was. We're going to take these two ideas and combine them into a single idea. What happens when we have this curve, or this region, bounded by two curves, and that starts to spin about the x-axis? We're still going to have a volume of revolution, looking at what we have on the right, but we're going to have part of this is going to be cut out and it's not going to be there. That's where we're going to have our washer method. So let's take a quick look at an example. Here, we're going to determine the volume of a solid formed when the area between two curves is rotated about the x-axis. Previously, as we had just seen, we can find the area between two curves. It was going to be the integral of the outer curve, the top curve, minus the inner curve. We're going to use the same idea. Once that rotates around, it's going to create this figure where it's going to be hollow on the inside. Our disk is actually going to be more of a donut, or what we like to call a washer. We're going to have an outer radius. In this case, it's going to be x, and we're going to have our inner radius. In this case, is going to be that x squared. The area of a single disk is going to be that outer radius minus the inner radius. It's going to be the outer radius, or pi r squared, excuse me, subtract pi times the inner radius squared. We'll get the area of that circular section. We're going to call this a washer, thinking nuts, bolts, construction, that kind of thing, a washer. Well, the same idea applies, whereas before our volume was the integral of pi r squared. Now we're going to be taking out that intersection, just like we had done previously when we looked at the area between two curves. I'm using this, our two functions are going to be x and x squared as examples. We have the intersection between those two, and they're going to intersect on the left at x equals 0. They're going to intersect at the right at x equals 1. So those are going to form the bounds for our integration. The disk method, we recall, is going to be pi times r squared dx. What's happening now is we have that full area, and we're going to take out the inner area. So our volume, when we're using washers, and so what we have now, our volume using washers is going to be pi, the integral from a to b of the outer radius squared, subtract the inner radius squared. And that's going to take that inner section out of the volume. So we have something in this case that looks somewhat like a cone. Let's go ahead and use this example that we're going to do. Our outer function, in this case, is x. Our inner function, in this case, is x squared, as seen in the curve up on the left. Our volume, then, is going to be pi multiplied by the integral from 0 to 1. Our bounds were determined based upon the intersection points. And we're going to have our outer radius, x squared, subtract our inner radius, x squared squared. I'm going to do a little math to neaten this up. That's going to get us pi multiplied by the integral from 0 to 1 of x squared minus x to the 4th dx. And that, in turn, we can evaluate that, giving us pi multiplied by 1/3 x cubed minus 1/5 x to the 5th, evaluated from 0 to 1. And all of that comes out to be, you can check this on your own, 4 pi over 5. So going back, when we have these washers, we're going to have pi multiplied by the integral of the outer radius minus the inner radius dx. There you go. Good luck.